Okay.
Okay, so hello everyone. So John Reppy is going to do this first session preview about parallelism.
Okay, thank you. This session will, of course, be, I guess, across the hall in the Kelvin lecture, get the room right. So there are 4 papers, and these papers the first 3 of these papers share a fairly common intellectual framework. The last paper is maybe a bit more of a standalone paper, although there's a lot of author overlap among them. So I would like to first just give a little bit of background about some concepts that are sort of key mostly to the first 3 papers. So these papers are all about the setting of nested parallelism. So this is irregular parallelism, task parallelism, and there are a lot of different terms you can use. It's not data parallelism is perhaps the key idea. And the key feature here is that parallel tasks can dynamically spawn other parallel tasks, right? So you get this kind of dynamic structure for the parallelism. And one concept that's come out of this space in the last, 10 or 15 years is this notion of what's called a computation graph, which is sort of a dynamic representation of that parallelism structure, okay? And so a lot of these papers, a lot of the ideas in these papers really refer back to this notion of the computation graph. So there are really 2 kinds of parallelism that we will see in these papers. So fork join parallelism, so you're going to have sort of diamond properties, but obviously nested diamond properties there, where a parallel task forks itself into 2 parallel tasks, and eventually those join back together. And then this notion of futures, which, futures are an extremely old idea. They go back to Multi-Lisp and Halstead's work in the 1980s. But they've been sort of rediscovered as a kind of nice way to deal with certain kinds of parallel structure that fork join parallelism is too limited for. Another key idea, which is a very recent idea, is this notion of what's called disentanglement. So this goes back to a POPL paper from just a couple of years ago. And the basic idea of this is that if you have race-free programs and you have this disentanglement property, then there's not going to be any interference between them. So it's a kind of a separation property about the parallel threads. And in the early work, disentanglement is a property that could be checked dynamically by basically looking at the computation graph. But in some of this more recent work that we'll talk about in a moment, people are starting to come up with more static approaches to understanding disentanglement. So I want to go over the 4 papers and just give a little bit of a discussion of what some of the highlights of each paper are. So the first paper is called Pipelines and Beyond, Graph Types for ADTs with Futures. So in POPL 2022, there was a notion of graph types were introduced by the 4th author here. And the idea of graph types is essentially it's a typing scheme for these computation graphs. So computation graphs refer to a specific parallel execution. Graph types refer to a family of computation graphs. And in the original work, graph types were kind of limited in what they could describe. In particular, they were limited to fork join parallelism, but now in this paper, they're extended to handle this kind of future parallelism. And the key aspect of this paper is that there's a type inference algorithm for this type system, so they can take like an OCaml program or a subset of an OCaml program and actually infer the graph type for the parallelism in that program. So the second paper is called Disentanglement with Futures, State, and Interaction. And so this, again, we see this word disentanglement. And so this builds on the previous work on disentanglement, which was basically limited to fork join parallelism, and by adding mechanisms to handle futures. So again, liberalizing the notions of the parallel structure of the programs, and also introducing I/O and dealing with certain classes of programs that actually communicate with the outside world. As before, as in the previous work, it shows that data race-free programs with futures are disentangled. So this is sort of the main technical reason why you want to have this property. And it also shows that even in the presence of certain classes of so-called weak races, programs are also disentangled. And there's a bunch of other technical results in the paper, but they won't fit on the slide. So I'm limiting myself to sort of 3 bullet points per paper. So, okay. So this paper is a little bit different in terms of what it's talking about, because these other papers are really sort of systems-y papers, and this one's very much a kind of a verification paper or a programming logic paper. But it tackles the problem of how do you know that your program has this disentanglement property? Because a lot of the previous work has relied on essentially informal reasoning and dynamic checks. So you can take the, at runtime you can look at the computation graph and you figure out, yes, this is disentangled, or no, there's a problem. So this work describes a program logic, and actually, technically, I guess 2 program logics for proving disentanglement in parallel programs, and this is all mechanized in Coq using the Iris, built on top of Iris. In the last paper, which is a distinguished paper, so this one it doesn't directly address disentanglement, but some of these ideas are sort of lurking in the background. This is really more focused on a problem that parallel functional language implementations have, which is that it's very easy to design a language and write programs that have incredible amounts of parallel work. And, it sort of comes with the territory of functional programming, right? You write a recursive function over a tree. At every node of the tree, you get 2 tasks that you could do in parallel, right? So you just get massive amount of work. And that's way more work than you're going to have processors for, and the overhead of managing all that work can swamp the parallel gains you get. So there's been a lot of work over the years, and in fact, the third author, who was my PhD student a number of years ago, for his thesis worked on exactly this problem of coming up with clever ways to do low overhead representations of potential parallelism in the program execution. And you combine that with, this is a runtime system, a runtime mechanism. You record that there's potential parallelism, and then the scheduler or work stealer or whatever is used to actually create parallelism and schedule jobs on the parallel processors. So this paper, takes us, well, there's been a lot of work since that earlier work, and this paper continues that line of research by describing a hybrid approach. So this is sort of combined compiler support and runtime system support. And the clever thing they came up with is a way of doing function calls with multiple return continuations. So you can do, you can effectively have these different return continuations corresponding to different states of the potential parallel work that's at that parallel call, and then the runtime system can effectively sort of walk back to the stack and choose which continuation to use, and there's a bunch of stack hackery you have to do to make that work. But it's extremely lightweight, which is key, so it keeps the overhead in the common case where there's no parallel work fast, and then they've combined this with work that they've been doing on scheduling and various runtime support, and the whole package ends up being an extremely efficient way of managing parallelism in a parallel functional language. And that's it.